Now, so we're covering the bitwise operators at the minute, and in this one we're going to look at the AND operator. And I always have trouble drawing it. I'm sure you do too. That's not it either. That's better. Do it slowly. Okay, so this is the AND operator. What we're going to do is we're just going to show a little bit of a program here. I'm going to say int x. I'm going to say int y. I'm going to say int z. Now what I'm going to do is I'm going to set x to be some value. So I'm going to say that it's equal to 7. And I'm going to say y is equal to, let's say, 9. Okay. Now, what we need to do here, I'm going to just do a little comment here, as if I was doing a comment in a C program. Let's just see what the binary numbers for those look like. So I happen to know them off in my head. Okay, so for 7, it's going to be 0, 1, 1, 1. And the reality is there's going to be a load of zeros in front of that as well, because integers take up much more space than we give them credit for in this case. Again, for the 9, I put a load of zeros here at the beginning, but the 9 is basically 1, 0, 0, 1, like that. Now, what happens if I say z is equal to x and y? What will z be? Well, what I'm going to do is I'm going to take these guys up here and let's have a look. I'm going to do the whole lot of the first byte of the number, although there's actually even more zeros on the front of this than we're showing here. So 0, 1, 1, 1, and the next one 0, 0, 0, 0, 1, 0, 0, 1. Now, when we add these two together, 1 and 1 together, if you remember back here, 1 and 1 together gives us, sorry, I'm looking at the XOR there, 1 and 1 together gives us a 1 out. So that's a 1. 1 and 0, well, here we have 1 and 0 gives us a 0 out. So that's a 0. That's the same in this one. And the 0 and the 1, again, it's the same thing. It's going to be a 0 out. 0 and 0 also gives us zeros out. So that leaves us with that number there. Okay. Which again we can divide in 4s. This one is clearly going to be a 0. What's this one going to be? 0, 0, 0, 1. 0, 0, 0, 1 is a 1 in either decimal or hexadecimal, so it doesn't matter which we're showing here. That's going to be a 1. So in effect, if we printed out z at that point, we would get a 1. I'm going to pause there and just write that little bit of a program and show you that that's what happens. Okay, so I've written the program there. I've got x, y, z. I've given x a value of 7, y a value of 9, z equals x and y. Remember, just a single ampersand used here because it's not a logical operator, it's a bitwise operator. And then I say z is %d to print out as a decimal integer and print out the z. Let's have a look at the result. And we can see that the result is z is 1. Okay, and that's exactly what we predicted. Let's have a quick look then what would happen with the OR operator. And what I'm going to do is I'm going to actually end the give me a moment. What I'm going to actually do instead is I'm just going to show you one other thing, and then I'll leave the OR operator for a different recording. So what we're going to look at is how this result can be used. So the result in this case is being used just to print it out, but could we use it in an if statement? Such as I've shown here. So if z is equal to 0. Okay. Now, clearly z in our previous case was not. Okay. So do a printf here. Okay, and we'll see that that won't work. So we'll see that we can see there that the printf there z is 0 has not printed out. Now you might be wondering why exactly would I be doing this. Well, here's the reason, and you're going to see a number of ones like this. Let's say, for example, that I want to test what a certain bit within this number is. Okay, so I've set x to be 7, and I want to know whether the second least significant bit, so this being the least significant, the least important bit, the second least significant bit, I want to find out if that's a 1 or a 0. So how I would do that is as follows. I would take my number x, put whatever number into it, 7 in that case, but I would then set y to be the following number. So I'm going to get rid of y there. I'm going to set y to be equal to the following: 0, 0, 0, 0, 0, 0, 1, 0. So I'm going to put a 1 in that bit. Now, need to check what number that will actually be. So 0, 0, 1, 0 is a 2. Okay. So I'm going to write this in hexadecimal. So I'm going to say 0x02. Okay. I could just put it as decimal 2, but I'm going to write it this way so that you get a little bit used to that. So what I now say then is x and y, and what will occur is the following. Our x value, as we've seen, is 0, 1, 1, 1. Our y value is as follows. Now, in all of the cases, 0, 0, that's going to be a 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 0, so is this one. For all of these as well, because we've got a 0 in there, we know that between the two of them they can't make a 1 output. This is the only one that possibly could. And in this case, I said 1 and 1 together gives me a 1. Now the answer there has come out as being a value of 2. And 2, I think you'll agree, is clearly not 0. So that can be used back in our program here to show whether the bit is a 1 or a 0. So let's write that. So 0x02. So I can change this to be the second least significant bit is 1. I can do an else on this. I can steal this printf. Okay, save that. Now, so we'll run that and we see that the second least significant bit is 0. Okay. Now, I think that's gone wrong with me because I think I have them in the incorrect places. So we'll just change that. That should actually be a 0 there. And that should be a 1. Because obviously if this has come up as 0, we don't expect it to happen. So there we say the second least significant bit is 1. And I see a spelling mistake there as well. So now, so let's try a number here that's second least significant bit is going to be 0. So let's go and take some from our values here. This is the second least significant bit, this one here in this column. So let's go and take this number here, which is the number 4. So that's 0, 1, 0, 0. That's the number 4. So I'm going to put in a number 4 here instead of 7. And let's run that. And we see that the second least significant bit is now 0. Okay, because that's what we've tested for. Now, we do happen to know that in the one that has a 4, that the third least significant bit here is a 1. Okay, we can see it there. So let's try for that one. So I'm just going to write third here just to prove it. Third. And so what we're going to do is we're going to test for the third least significant bit. that means changing that to a 4, okay, because it's going to be 1, 0, 0, and when we run that, we can see that that has come out as a 1. So you'll get used to doing it. I'm going to do a number of exercises with this. You might be wondering where exactly would we use this. Well, if you're covering the microcontroller, the 8051, in some of the other subjects, then you'll be coming across this a lot. In many cases you have a register, it could be the PCON register, the TMOD register, any of these registers that we use. And individual bits mean different things within them. So sometimes we need to test whether an individual bit is a 1 or a 0 in order to determine what we should do next. And therefore this sort of thing is very useful for actually finding that out. Okay, so that's the logical, or the bitwise, and in the next video I'll be showing you the bitwise OR.